In this video, I'm going to give you some tips for Achieve Homework 3. Question number 1 is just asking you to draw the structure of an ether. This is using IUPAC nomenclature, so the ether group here is the methoxy group. Question number 2 is asking you to draw the product of this particular reaction, this formation of an ether. Notice that it wants you to draw the non-bonding electron pairs. That's going to be the lone pairs of electrons on the oxygen over here in your product. And it says to clearly indicate the stereochemistry. It says using a wedge, dash, and 2 in-plane bonds. What that means is obviously the wedge, the dash, and 2 in-plane bonds. That's what I refer to as the straight line bonds. In terms of the stereochemistry, you've got 2 chiral carbons in this molecule, and if you pay attention to the mechanism, if you notice on the mechanism, you're not actually doing anything to either of those chiral carbons. You're reacting this oxygen with this carbon right here, but the chiral carbons are not being affected, which means that it is impossible for you to be doing anything with their stereochemistry, aka these stereocenters should not change. The chirality of those carbons can't change because you're not doing any chemistry to them. Question number 3 is just asking you to predict the products. Of course, it's not listing the actual reagent that you would need to do this reaction, but it just wants the structure of an alkyl bromide and then an alcohol that you could combine using the right reagent to give you that ether right there. Question number 4 is just asking you to draw curved arrows. It's got all of the reactants and products. Everything is shown for you, so you're just going to look at what you're starting with, look at what your next step produces, and then just fill in the curved arrows as needed. And I think there's a total of four boxes here. But again, all you're doing is curved arrows. You're not actually drawing any products or reactants. Question number 5 is a multi-step reaction. My suggestion always with these is that you start by finding the structure of your reactant, bromocyclopentane, that looks like this guy right here, and then your product, 1,2-epoxy cyclopentane. Now, I don't go over the nomenclature for epoxides in class, but the term epoxy means that it is an epoxide, and there is only one of them available here, and hopefully the name sort of makes sense. It's a cyclopentane, and we've got a cyclopentane, and then we've got an epoxy, and the 1 and the 2 just refers to the position of the epoxide on the ring. But if you were really uncertain about that, you could just Google 1,2-epoxy cyclopentane, and then you would find that this is the structure. And then you're just going to fill in the necessary reagents and the intermediates that will perform this transition for you. Question number 6 is asking you to draw the product of a ring opening reaction. A couple of tips with this. So the first tip I'm going to give you is that we are working with the cyanide base in this reaction, which is kind of, I don't know if I want to call it a functional group, but it is a polyatomic ion for sure. And you don't have a cyanide button over here. You have a carbon and a nitrogen button, which means that you're going to have to enter the cyanide ion as a carbon and nitrogen. You're going to have to draw that thing out. It's a carbon triple bonded to a nitrogen with a lone pair of electrons on the nitrogen. And that carbon is going to be attached to, whatever part of this molecule you're attaching it to. So this is a base ring opening reaction. The sodium is just a spectator ion, so you can just kind of ignore it. I put that negative charge next to the nitrogen, but it really belongs next to the carbon. And then the ethanol and the water, those are just solvents, so you can ignore them. So in terms of drawing the product of this reaction, you want to look up, if you're dealing with a base ring opening under basic conditions, you want to look up which carbon is going to be attacked in the epoxide, and then also what's going to happen to the stereochemistry, because you've got to show the stereochemistry in your product. And then also make sure you're getting that cyanide, that group, drawn out with its triple bond. Next one, similar question. This one is also a base ring opening under basic conditions. The methanol down here, that's just your solvent, so you're going to ignore it. And this is the molecule that you are using to open the ring, so you want to look up which carbon is going to be attacked in this reaction, which carbon is the base going to attack. And notice that you don't have to show stereochemistry for this one, you just got to get it drawn in the right spot. And then we have an acid catalyzed ring opening reaction. For this one, the H3O plus is the catalyst. This is the part that's actually, this right here is the part that's actually making the reaction happen. So you can kind of ignore it. You know, if you want to draw the mechanism of the reaction out sort of for yourself to help you figure it out, then you would need to pay attention to that H3O plus. But if you're thinking about what are you actually adding or what is actually attacking, it's the H2O molecule that is actually doing the attacking in this reaction. With an acid catalyzed ring opening reaction, you want to look in your notes, ask yourself which carbon is going to be attacked. We have a secondary carbon versus a tertiary carbon. Which carbon is going to be attacked in this reaction? And then also what happens to the stereochemistry, because you do need to show stereochemistry here. For the next one, this one's also acid catalyzed ring opening, and H2SO4 is our acid, so we're going to kind of ignore that. It's the methanol CH3OH that's actually being added. Again, same questions. Ask yourself under acidic conditions, this is an acid, which carbon atom is going to be attacked and what's going to happen to the stereochemistry. And then we have another one. So this is one where the reagent, HBr, this serves as the acid as well as the substance that's opening the ring. So I'm not going to cross anything out because all of it is important. Another acid catalyzed ring opening, same questions. Which carbon is going to be attacked? What's going to happen to the stereochemistry of that carbon? Don't let this one freak you out. Like, it's got this extra ring on here, and if that stresses you out, you can just kind of ignore it for the time being and just sort of think about it like this molecule right here. And then once you've got your product sketched out in the end, go ahead and put that ring back in the product. Don't let that extra ring make you think that something unique or different or special is going to happen. This guy's going to react the same way as all the other acid catalyzed ring opening reactions. Now we have a few multi-step reactions. We want to start by filling in your reactant and your product. These are both alcohols, so you should have no problem finding them down here. The names are really similar. One is 3-methyl-2-butanol and the other is 2-methyl-2-butanol, so just make sure that you're getting the right molecule in the right spot. Two molecules that are going to be constitutional isomers, and then you're just going to fill everything in the rest of the way through. We have another similar-ish multi-step reaction. This one you actually have to draw the products and the intermediates. It's giving you a hint. It says you're going to start with a cycloalkene, meaning that you need to have a carbon-carbon triple bond. And it's also telling you that it is C6H10. Now, don't just automatically assume that it's going to be this guy right here. If you look, because this is C6H10, but if you look at the structure of the product you're trying to make, that's going to be a really difficult transformation to start with a 6-membered ring and end with a 5-membered ring. So probably what we're going to be starting with is a 5-membered ring that has a double bond in it, and then it's going to have carbon number 6 coming off of that ring somewhere as a methyl group, and you need to decide where that methyl group is located, and look ahead at the product. That's going to help you make a decision about where the methyl group should go. If you know that you're starting with an alkene and you're trying to convert it into a vicinal diol, a side-by-side diol, just take a look at the reactions you've been learning in this chapter, and what reactions have you learned that will produce two OH groups side by side. And that should help you figure it out. Now, one thing I'm not showing here, if you scroll all the way down, there are some pull-down menus for you to select the reagent 1 and reagent 2 from a list of possible reagents. This is showing you a transformation, and then you just have to pick the 2 reagents that are necessary for this transformation. So let's take a look at exactly what's going on here. Obviously, we're getting rid of the double bond, and also we're adding an OH group, and we're adding a methoxide group as well, both of those at the same time. When we're ultimately adding 2 oxygens to a molecule in a side-by-side configuration, I usually think of a ring opening reaction. The ring is going to give us an OH from the oxygen in the ring, and it's also going to give us an O, whatever we choose to add. So this would be a ring opening using OCH3-. That's a huge hint that I just gave you. So you need to look at these reagents and figure out which one of them is going to create an epoxide, and then which one of them is going to open an epoxide. And then we've got another multi-step reaction. Again, start by filling in your reactant in your final product, 2-methyl-2-butene, which you should have no problem finding, and then 3-bromo-3-methyl-2-butanol. Both of those you know how to name, so you should be able to proceed with that. All of these are familiar looking molecules. And then last but not least, this problem is pretty, well, it looks pretty tricky. I've got it on 2 slides. This is what the problem actually looks like, and you've got to fill in these 6 boxes. You've got 8 options, which means you're going to use 6. 2 of them are not going to be used. And you've got all of these hints to sort of help you figure out what these reagents are. Now, really, the only place that you can start this little roadmap problem is right here. Obviously, you know, it would be really difficult to start here or start here because you don't really know where you're coming from, but you are going to start here or here, A and B, and think about using lithium aluminum hydride. What could you start with that would give you this molecule? Now, one of the challenges with this problem is that clearly there are two options from this list. There are 2 things that are going to give you LAH. You're going to find 2, and you're going to put one of them in box A and one of them in box B, and it's not going to matter which one you put where. These 2 molecules, A and B, it's giving you a hint over here. Their formula is C7H12O, which means when you're looking at your list, because I'm going to make a note of that right here, C7H12O, that's the formula for molecule A and also for molecule B. So for like this guy right here, which has 2 oxygens, it can't be that one. And here's another one with 2 oxygens. It can't be that one either. So I've got 2 of them eliminated for you. It's 2 of these guys. Check the formulas of each one of these molecules before you do anything else, and make sure you're finding ones that have the formula C7H12O. Also, another hint, it tells you that the compounds have, A and B, have identical physical properties. Same melting point, same boiling point. They appear to be optically active, rotating light in opposite direction with equal magnitude. This means that they are enantiomers of each other. It's been a long time since we talked about this, way back in chapter 5. Enantiomers are the mirror image molecules that rotate light in opposite direction. So that means that A and B must be enantiomers of each other, mirror images of each other. So that means it wouldn't make sense to choose one of these as A and the other one as B because they're not enantiomers of each other. But it would make sense, let's say, to choose these 2 because they are enantiomers of each other, or these 2 also, or these 2 right here, also enantiomers of each other. Now, once you get these 2 molecules filled in, the rest should be pretty straightforward. You're going to do a Grignard reaction right here to give you E and F. You're going to react with H3O plus to give you this molecule here. I do want to point out this is a reagent that our textbook does not use, so it's unfamiliar to you. But you don't really need to know what this is in order to be able to fill in C and D, because you're going to fill it in based on that reaction. But I will let you know that this reagent right here reacts with vicinal diols. So that would be molecules that have OH groups on adjacent carbons, and it converts them, HiO4, it breaks that carbon-carbon bond, and it converts those oxygens into carbonyl groups right there. So it breaks the carbon-carbon bond, and it converts the carbon oxygens into carbonyl groups. And maybe looks a little better if I put some extra carbons on there as well, because it just looks kind of funny without them. So we'll go like that. And again, you don't really need to know what that is to be able to do this problem, but this molecule right here and this molecule right here, they should be vicinal diols. That's another way that you can double check that you're getting these structures correct. So with all of those hints, even though this problem looks super intimidating, it's probably going to be pretty easy for you to straighten out. And if you get the problem wrong, the advice that I would give you is to just double check that you have all of your molecules lined up correctly. Like these molecules should be enantiomers of each other. These molecules should also be enantiomers of each other, and these two will also be enantiomers of each other. But the one thing that you need to double check on is, for this molecule turning into this molecule, is the stereochemistry correct? Or maybe do you have these two molecules in the wrong spots? Same going this way. Is the stereochemistry of this product correct? Or is it possible that you mixed up these two molecules with each other? So those would be a couple things that I would double check if I got this problem wrong.